Mast Electronics. Today we are going to design an electronic thermometer using LM741 op-amp as dual comparator with NTC Thermistor. First, let us go to the power supply section where we are having two voltage sources V1 and V2. V1 will be providing plus 12 volts and V2 will be providing minus 12 volts. So I am going to feed these two voltages to my op amp. These supply voltages allow the op amp output to swing toward both positive and negative saturation levels. In this circuit, the comparator outputs can reach approximately plus 11 volts and minus 11 volts. This is important because the comparator must clearly indicate on-off conditions. Now let us move to the sensing section. The circuit uses a 10 kilo ohm NTC thermistor. NTC stands for negative temperature coefficient. VA equals 12 multiplied by the thermistor resistance divided by the sum of R2 and the thermistor resistance. At low temperatures, the thermistor resistance is high. Node A voltage is also high. At high temperatures, thermistor resistance decreases. Node A voltage also decreases. Therefore, temperature is converted into a voltage signal. The thermistor behavior is modeled mathematically using the B parameter equation. In this circuit, R0 equals 10 kilo ohms, T0 equals 25 degrees Celsius and B equals 3950 Kelvin. This equation is directly implemented inside LTspice using a behavioral resistance expression. As a result, the thermistor behaves very similarly to an actual physical NTC device. Next, let us discuss the hot reference voltage. Resistors R5 and R6 form a voltage divider. These resistors generate the voltage reference called hot reference. The calculated value is approximately 2.79 volts. This voltage represents the hot temperature threshold. Similarly, resistors R7 and R8 generate the cold reference voltage. The value obtained here is approximately 7.71 volts. This voltage represents the cold temperature threshold. Now let us understand the comparator operation. The LM741 is normally used as an operational amplifier. However, when it is used without feedback, it behaves as a voltage comparator. The LM741 has a very high open loop gain. Therefore, even a very small difference between the two input voltages forces the output to either positive saturation or negative saturation. Let us first look at U1. This comparator detects high temperature. The non-inverting input receives the hot reference voltage. The inverting input receives node A. At low temperature, node A is greater than the hot reference. Therefore, the output remains negative saturation. As temperature increases, node A decreases. When node A becomes lower than 2.79 volts, the comparator output switches to positive saturation. This turns on the red LED. Then coming to the cold comparator operation, now let us look at U2. The non-inverting input receives node A. The inverting input receives cold reference. At low temperatures, node A is greater than 7.71 volts. Therefore, the output becomes positive. As temperature increases, node A decreases below the cold reference voltage. The comparator output switches to negative saturation. The blue LED turns off. Therefore, the blue LED indicates cold condition. Now, let us discuss the simulation commands. Step parameter temperature from 0 to 100 with a step size of 1. LTspice automatically changes the temperature from 0 degrees Celsius to 100 degrees Celsius with an increment of 1 degree. Therefore, more than 100 operating conditions are analyzed automatically. This allows us to study the entire temperature range in a single simulation. The .op command, operating analysis. Since the circuit contains only DC signals, no transient analysis is required. For every temperature value, LTspice calculates node voltages, comparator outputs, LED states. This makes the simulation very fast and computationally efficient. Now let us run the simulation. So here I am clicking the run or pause button. Let us see what is the result. There you go. We get the output. The green curve represents the sensor voltage VA. At 0 degrees Celsius, the voltage is approximately 9.3 volts. At 100 degrees Celsius, the voltage decreases to approximately 0.85 volts. This confirms the correct operation of the NTC thermistor. The blue waveform represents the cold comparator output, while the red indicates the hot comparator output. Below approximately 12 degrees Celsius, the blue LED remains on. At around 12 degrees Celsius, the output switches sharply. The blue LED turns off. The red waveform represents the hot comparator output. Below approximately 55 degrees Celsius, the output remains in negative saturation. At approximately 55 degrees Celsius, the red LED turns on. Therefore, the entire temperature range can be divided into three regions. From 0 to 12 degrees Celsius, the system indicates too cold condition. From 12 to 55 degrees Celsius, the system remains normal. Above 55 degrees Celsius, the system indicates too hot condition. We see there is a voltage difference. This is because of the voltage drops across the LEDs. So in this video we successfully designed and simulated an electronic thermometer. Thank you for watching. If you found this video useful, please like, share and subscribe to the channel. See you soon in the next video. Thank you.